Archival footage of burning Israeli Centurion tanks in the Sinai, 1973 Yom Kippur War. Slow-motion simulation of a shaped-charge warhead detonating. Cut to black. October 6, 1973. Egyptian infantry fires Soviet Sagar missiles at Israeli armor. In seconds, a copper cone collapses into a molten jet traveling 8 to 10 kilometers per second. The jet doesn't punch steel, it hydrodynamically displaces it. Traditional homogeneous steel armor, no matter how thick, fails the same way every time. That single physics problem, the Munroe effect, made main battle tanks look obsolete overnight. Yet right now, in early 2026, U.S. elite troops from the 82nd Airborne and M1 Abrams tanks are flowing into CENTCOM bases in the Middle East. Why ship 70-ton monsters halfway around the world if the physics says they should die to the first modern anti-tank missile? The answer is not better steel. It's better materials. Map of CENTCOM region highlighting current tension zones, Strait of Hormuz, Red Sea, Iraq/Syria border. Overlay of U.S. prepositioned stocks and recent C-17 airlift flights. The driver is brutally simple. Peer and proxy forces now field thousands of advanced anti-tank guided missiles and explosively formed penetrators. Light infantry, even elite paratroopers, cannot hold ground against that without heavy armor. The M1 Abrams is the only Western tank whose frontal arc still offers a realistic chance of surviving first contact. But getting it there exposes the real engineering story. High-speed Schlieren photography of shaped-charge jet formation, side-by-side animation, APFSDS tungsten rod versus ceramic target, slow-motion molecular-level stress/strain simulation. At the moment of impact, two completely different threats hit the armor. Shaped charge jets heat warheads, a 7 to 10 km/s fluid metal jet that exerts pressures of hundreds of thousands of atmospheres. Steel simply flows out of the way. Kinetic energy penetrators, APFSDS darts, long rods of tungsten, or depleted uranium moving at 1.5 to 1.8 km/s. Their kinetic energy is measured in megajoules. The fundamental limit is material behavior at extreme strain rates. Most metals become plastic. They deform and lose strength. Ceramics, however, stay rigid until they shatter. And that shattering is exactly what we want. Exploded 3D cutaway of M1A2 SPV3 turret armor. Layer by layer animation. Outer steel. Ceramic tiles. DU mesh backing plates. Spall liner. Real-time CFD-style simulation of jet disruption. Enter Chobham composite armor. First developed in the UK, perfected by the U.S. for the Abrams. It is not one material. It is a carefully sequenced sandwich. Outer steel plate catches fragments. Tiles of high-hardness ceramics, boron carbide, silicon carbide, or alumina. Depleted uranium alloy mesh or plates in the heavy variants. Rubber or Kevlar spall liner on the inside. When the shaped charge jet strikes the ceramic, the tile fractures in a cone pattern. The jet has to push aside billions of tiny, ultra-hard fragments. Each fragment steals momentum and destabilizes the jet's coherent flow. The jet mushrooms and breaks up before it reaches the steel backplate. For kinetic rods, the depleted uranium layer does something even cleverer. Uranium's density, 19.1 G/cm superscript 3, is 70% higher than lead. When the rod hits, the DU deforms plastically but stays coherent longer than tungsten. It also ignites on impact, a pyrophoric effect that adds localized heat and pressure, literally eroding the incoming penetrator from the sides. The rod self-sharpens as it loses mass unevenly. Result: the M1A2's frontal armor is rated to defeat the best Soviet era and early Russian threats. That is why the tank is worth the logistical headache of moving it into theater. Side-by-side weight comparison graphic. M1A2 almost equals 68 tons versus T90 almost equals 46 tons. Fuel consumption graph. Abrams 2 gallons per mile cross-country versus diesel tanks. Desert sand ingestion animation on AGT 1500 turbine. See 17 loading sequence footage. But real engineering is compromise. Weight, 65 to 70 tons combat loaded. That single number dictates everything downstream. Strategic airlift is possible but painful. AC-17 can theoretically carry 1 Abrams, but you're pushing the aircraft to its structural limits. Most deployments still rely on fast sealift. Once on the ground, every bridge, every road, every recovery vehicle must be rated for that mass. The Honeywell AGT 1500 gas turbine engine gives 1,500 horsepower and ridiculous acceleration, but is horrifically thirsty. Roughly 2 gallons per mile in combat. In the desert, sand ingestion forces frequent filter changes. The turbine's high exhaust temperature also creates a massive thermal signature for infrared-guided missiles. Each M1A2 costs roughly $8 to $10 million before upgrades. The depleted uranium armor requires specialized handling and disposal protocols. The ceramic tiles must be manufactured to sub-millimeter tolerances or the entire stack fails. In short, the Abrams survives the physics of modern anti-tank weapons, but only by pushing every other engineering limit, weight, fuel, logistics, and budget to the edge. 82nd Airborne paratroopers, fast roping versus Abrams unloading from a ship in a Middle Eastern port. Logistics flow diagram showing preposition stocks plus surge air/sea lift. This is why the current 2026 deployment is such a statement. The 82nd Airborne can arrive in hours with nothing heavier than a Humvee. The Abrams arrives days or weeks later, either flown in small numbers or drawn from preposition stocks already in theater. The materials science victory and the turret buys time for the rest of the force to catch up. Gulf War 1991 kill ratio graphic. Abrams versus Iraqi T-72s. Modern urban damage footage from Iraq 2003 to 2011 with honest voiceover. Cost per tank lifetime graphic. Is this technology viable for the future? Yes, when the mission demands surviving the first shot. The 1991 Gulf War proved it. 0 Abrams lost enemy tank fire, but urban fighting and drone-launched top-attack munitions have shown the flanks and roof remain vulnerable. The armor is not magic. It is a calculated bet on frontal engagement. Sustaining a single Abrams battalion in the desert can cost tens of millions per month in fuel and maintenance alone. That is the price of pushing materials science to its current limits. Slow zoom out from a single Abrams silhouette against a desert sunrise to a wide-shot combined arms formation, infantry, tanks, aviation. Fade engineering blueprint style. We keep building heavier, more expensive armor not because we love tanks, but because physics still favors mass and layered energy absorption over pure electronics in the most contested environments on Earth. The M1 Abrams is not the future. It is the best compromise we have right now against immutable laws of ballistics and material science. And right now, that compromise is on a ship or an AC-17 headed to the Middle East. Thanks for watching. If you want the deep dive on the AGT 1500 turbines, thermodynamics, or next-generation ceramic matrix composites, drop it in the comments. Like, subscribe, and I'll see you in the next one, where we ask the hard engineering questions no one else will.